Good day, I am W. Frederick Jr. and here we are going to tackle about the manufacturing of electronics and semiconductors. What is electronics? Electronics is the study of flow of electrons in various materials or space subjected to various conditions. In the past, electronics dealt with study of vacuum tubes or thermionic valves. Today, it mainly deals with flow of electrons in semiconductors. Electronics in these days is what we use, everyday use, such as cell phones, televisions, radios, computers, laptops. Those are the product of electronics, or those are electronics. Bill of materials. It is a comprehensive inventory of raw materials, assemblies, sub-assemblies, parts and components, as well as the quantities of each needed to manufacture a product. So, bill of materials is the recipe of a certain product. Here, it is listed of what type of component, it is the selection of components, the quantity of each components to be used in the product, the assemblies, the raw materials, what are those, what are these. It is where the list and the cost of the products to be used in the to manufacture to manufacture a product. Designing is to create a structure of the concept that are planned beforehand. It focuses on the product's production components, cost, profit margin, performance, features, development feasibility, and manufacturability. Here in designing, it first in design is to produce this system block diagram, or this is the schematic diagram of your product, of the electronic. Next is the selection of production components, no? So mangita ka og parts say necessary for the product, or the components to be used in the product.
And now, we are down to testing. Accurate and stable testing and measurement is a critical aspect in all stages of semiconductor manufacturing in order to ensure accuracy and stability of the product. So next, today, with a number of design and fabrication companies involved in semiconductor manufacturing, the per part recurring costs have become a very important issue. The industry aims to bring down this by reducing the cost of testing, either at the design and manufacturing stage. These costs largely upon the time taken for testing and verification. So for testing, it has its test requirements. So there are three stages. So first stage is the manual characterization of the device, where its S parameter data is measured to frequency extremes, along with the manual calibration and measurements. So the second is the evaluation stage, where no measurement is required. Here, the device's performance is evaluated to decide the product specification. Then comes the final product testing. So the final product testing at the fabrication stage, where the device is checked for whether it meets the specifications. This stage is supported with automated calibration and testing. The other aspect of testing is to ensure the compliance and the interoperability of the final product based on the standards like HDMI, PCI, PCI Express, USB, and etc. And now we are on the assembly, testing, and packaging. Starts with cutting a finished wafer, which contains dozens of chips in a grid pattern after fabrication, into separate chips as illustrated in the figure below. Each chip is mounted on a frame with wires that connects the chip to external devices. and enclosed in a protective casing. These procedures, these, pr- these produce the final look of a dark gray rectangle with petal pins at the edges, which we can see in the third image in the figure below. The chip is also tested to ensure it operates as intended. ATP also requires various SME and materials. In reality, each individual step is highly complex, requiring several sub-steps, and the automatic precision of the fabrication process requires clean room clear of dust, particles which can interfere with chip fabrication.
Good day, everyone. We are going to talk about semiconductors. As you may not know it, the software you're using right now in viewing our report, or perhaps you're using your PC, is filled with semiconductors. So, what are semiconductors? From the word semi, what is semi? So, not Sir Semi, but it is describing the property, or it is describing its property. So, property to what? So, well, it's property to conduct. That's why it's semiconductors. So, conduction is a property of a material to let energy pass through, in this case, electricity. A semiconductor falls between a conductor, the ability of a material to conduct or to let electricity flow, and an insulator, or a material's property to resist the flow of electricity. It is special in a way because altering its properties by doping or introducing impurities can be utilized in useful ways. Structurally speaking, when two different dope regions exist in the same crystal, then it creates a semiconductor junction. So where can you find semiconductors in the periodic table? So you can find, or examples of semiconductors are found in the metalloid staircase. It is highlighted with the red boxes in the periodic table presented in the video. So examples are the following: silicon, germanium, or silicon and germanium. So what are the examples or uses of semiconductors? So being able to modify or alter the properties of a semiconductor can produce many useful products. For example, being able to let electrons pass on one direction to pass on with great number or with great electrons on one direction, and to be able to resist the flow of electron on the other side can be a good thing for amplification, switching, and energy conservation. So examples of these are found in our modern electric circuits, for example, diodes, transistors, and most modern electronics. So hearing about what are semiconductors and its uses, the question now is, how is it made? So it starts in what? Wafer processing. Fewer people know all semiconductor processes starts with a grain of sand, because the silicon contained in sand is the raw material needed to produce wafers. A wafer is a round slice formed by cutting a single crystal column made of silicon or gallium arsenide. To extract high purity silicon material, silica sand is required, a special material with a silicon dioxide content of 95%, which is also the main raw material for making wafers. Wafer processing is the process of making and obtaining wafers. So the first step is ingot casting or ingot casting. First, the sand needs to be heated to separate the carbon monoxide or CO and silicon Si, and the process is repeated until the ultra-high purity electronic grade silicon or EGSI is obtained. High purity silicon then melts into a liquid and later on solidifies into a single crystal solid formed an ingot. Later on, a picture of a silicon ingot will be shown, which is the first step in semiconductor manufacturing. It is also good to note that manufacturing precision of silicon ingots is very high, reaching to the nano level. After ingot casting is ingot cutting. After the previous step is completed, you need to cut off both ends of the ingot with a diamond saw. It is important to use a diamond saw because it is hard enough to cut through the ingot cutting or the ingot itself, and then cut into slices of a certain thickness. The diameter of the ingot slice determines the size of the wafer. Larger and thinner wafers can be divided into more units, which helps reproduce production cost. After cutting the silicon ingot, it is necessary to add a flat area or indent mark on the slice so that it is convenient to set the processing direction based on its standard in the subsequent steps. After all those steps, it needs to be polished. That's why the last step is water surface polishing. The thin slice obtained through the above-mentioned cutting process is called a die. That is an unprocessed raw wafer. The die surface is uneven and it is impossible to directly print circuit patterns on it. Therefore, it is necessary to first remove surface defects through grinding and chemical etching processes. Then, form a smooth surface through polishing and then cleaning residual contaminants.
The next part is oxidation. The role of the oxidation process is to form a protective film on the surface of the water. It can protect the water from chemical impurities, prevent leakage current from entering the circuit, diffusion during ion implantation, and the water from slipping off during etching. The first step of the oxidation process is to remove the impurities and pollutants, such as organic matter, metals, and evaporation residual moisture with 4 steps. After cleaning is completed, the water can be placed in a high temperature environment of 800 to 1200 degrees Celsius, and a layer of silicon dioxide is formed by the flow of oxygen or vapor on the water surface. Oxygen diffuses through the oxide layer and reacts with silicon to form oxide layers of different thicknesses, which can be measured after the oxidation is complete. Now we have two methods of oxidation. We have dry and wet oxidation. As you can see in the picture, dry oxidation method requires oxygen that runs in slow speed and has thin oxide layer, while in wet oxidation method, it uses water vapor and is fast and has thick oxide layer. In addition to the oxidizer, there are other variables that affect the thickness of the silicon dioxide layer. First of all, the wafer structure, surface defects, and the internal doping concentration will affect the rate of formation of the oxide layer. In addition, the higher the pressure and temperature generated by the oxidation equipment, the faster the oxide layer will be formed. In the oxidation process, it is also necessary to use dummy wafers according to the location of the wafers in the unit to protect the wafers and reduce the difference in oxidation degree. The next one is photomask. Photomask is the use of light to print circuit patterns into a wafer. We can understand it as semiconductor parts drawing on the surface of the water. The higher the fineness of the circuit pattern, the higher the integration of the product chip, which can only be achieved through advanced photomask technology. Specifically, it can be divided into 3 steps: photoresist coating, exposure, and development. First is the coated photoresist. The first step in drawing a circuit on a wafer is to coat photoresist on the oxide layer. Photoresist changes the chemical properties of the wafer to become a photographic paper. The thinner the photoresist layer on the surface of the wafer, the more uniform the coating, and the finer the patterns that can be printed. In addition, this step can use the spin coating method. The second one is exposure. After covering the photoresist film on the wafer, the circuit can be printed by controlling the light irradiation. This process is called exposure. We can selectively pass light through the exposure equipment. When light passes through the mask containing the circuit pattern, the circuit can be printed on the wafer coated with a photoresist underneath. During the exposure process, the finer the printed pattern, the more components can be accommodated in the final chip, which helps to improve the production efficiency and greatly reduce the cost of individual components. The last one would be development. The step after exposure is to spray developer on the wafer in order to remove the photoresist in the area not covered by the pattern so that the printed circuit can be revealed. After the development is completed, it needs to be checked by various measuring equipment and optical microscopes to ensure the quality of the drawing of the circuit diagram.
So the next step in manufacturing semiconductor is etching. After the photolithography of the circuit diagram is completed, on the wafer, an etching process is used to remove any excess oxide film and only the semiconductor circuit diagram is left. To do this, liquid, gas, or plasma is used to remove the unselected parts. There are two main etching methods depending on the materials used. Wet etching that uses specific chemical solution for chemical reaction to remove the oxide film, and dry etching that uses gas or plasma. So what is wet etching? Wet etching that uses chemical solution to remove oxide films has the advantage of low cost, fast etching speed, and high productivity. However, wet etching has the characteristics of isotropy. That is, its speed is the same in any direction. This will cause the mask or sensitive film and the etched oxide film to not be completely aligned, making it difficult to process very fine circuit diagrams. Next is dry etching. Dry etching can be divided into three different types. The first is chemical etching, which uses etching gas, mainly hydrogen fluoride. Like wet etching, this method is also isotropic, which means that it is not suitable for fine etching. The second method is physical sputtering. That is, ion in the plasma are used to strike and remove excess oxide layer. As an isotropic etching method, it has different etching speeds in the horizontal and vertical direction. So its fineness must exceed that of chemical etching. However, the disadvantage of this method is that the etching speed is slow because it completely relies on the physical reaction caused by ion collision. The third method is reactive ion etching, or RIE. It combines the first two methods. That is, while using plasma for ionized physical etching, and chemical etching is performed with free radicals generated after plasma activation. In addition to the etching speed exceeding the first two methods, RIE can use the characteristics of ion anisotropic to achieve high definition pattern etching. Now, dry etching has been widely used to improve the yield of fine semiconductor circuits. Maintaining the uniformity of full wafer etching and increasing the etching speed are crucial. Today's most advanced dry etching equipment is supporting the production of most advanced logic and memory chips with higher performance. So the next step in manufacturing semiconductor is etching. After the photolithography of the circuit diagram is completed, on the wafer, an etching process is used to remove any excess oxide
film, and only the semiconductor circuit diagram is left. To do this, liquid, gas, or plasma is used to remove the unselected parts. There are two main etching methods, depending on the materials used. Wet etching that uses specific chemical solution for chemical reaction to remove the oxide film, and dry etching that uses gas or plasma. So what is wet etching? Wet etching that uses chemical solution to remove oxide films has the advantage of low cost, fast etching speed, and high productivity. However, wet etching has the characteristics of isotropy. Isotropy. That is, its speed is the same in any direction. This will cause the mask or sensitive film and the etched oxide film to not be completely aligned, making it difficult to process very fine circuit diagrams. Next is dry etching. Dry etching can be divided into three different types. The first is chemical etching, which uses etching gas, mainly hydrogen fluoride. Like wet etching, this method chemical vapor deposition is the precursor gas chemically reacts in the reaction chamber and generates a thin film attached to the surface of the wafer and byproducts that are drawn out of the chamber. Plasma-enhanced chemical vapor deposition requires to use plasma to generate reactive gas. This method reduces the reaction temperature that is very suitable for temperature-sensitive structures. In addition, the use of plasma can also reduce the number of depositions, which can often lead to higher quality films. The next one is the atomic layer deposition. The atomic layer depositions form a film by depositing only a few atomic layers at a time. The key to this method is to loop the independent step in a certain order to maintain good control. Coating the precursor of the wafer surface and the first step, after which different gases are introduced to react the precursor to form the required substances on the wafer surface. And the last one is physical vapor deposition. Physical vapor deposition refers to the formation of thin films by physical means. Sputtering is a physical vapor deposition method. Its principle is that atoms of the target materials sputtered out by the bombardment of argon plasma and deposited on the wafer surface to form a thin film. In some cases, the deposited film can be treated and improved by techniques such as ultraviolet heat treatment.
So the next process is called interconnection. So the conductivity of semiconductors is between conductors and non-conductors uh, or insulators. So this characteristic allows us to fully control the current through wafer-based lithography, etching, and deposition processes. Transistors and other components can be constructed, but they also need to be connected to achieve power and signal transmission and reception. So that's why the next process is called interconnection. So metal is used for circuit interconnection because of its conductivity, which is needed to meet the following conditions. So these conditions are needed to be met para sa for us to continue or to go with the next process. So the first that we should consider is the metal should be, or the circuit should be low resistance. So since the metal circuit needs to pass current, so basic, the metal in it should have low resistance. So it's basic. Next is thermochemical stability. So the properties of the metal materials must remain unchanged during the metal interconnection process. So if the metal in the circuit will change or will have no stability, so it is not a good na ipadayon pa nato. No? Next to consider is
It should be high reliability. No? So with the development of integrated circuit technology, even a small amount of metal interconnect materials must have sufficient durability. So dapat ligod yun na siya. No? And the next is manufacturing manufacturing cost. Manufacturing cost. Even if the previous three conditions have been met, high cost is not suitable for the mass production. So even though kaning low resistance, thermochemical stability, and high reliability are met, so it is not good kung sobraan na siya kamahal. So another thing to consider is the manufacturing cost. No? So in continuation, the interconnection process mainly uses two substances, the aluminum and the copper. No? So in aluminum interconnect process, this process starts with aluminum deposition. So photoresist application and exposure and development. So removing any excess aluminum and photoresist before entering the oxidation process through etching tech. So after the forging steps are completed, we should repeat them until the interconnection is completed. So with its excellent electrical conductivity, so aluminum is also easy to lithography, etch and deposit. Now that is the good thing of aluminum. So in addition, it has a lower cost and better adhesion to the oxide film. The only disadvantage is that it is easy to form. It is easy to corrode and has low melting point. And also, in order to prevent the reaction of aluminum and silicon from causing connection problems, it is also necessary to add metal deposit to separate the aluminum from the wafer, which is called barrier metal ang tawagan. No? So, aluminum circuits are formed by depositions. After the wafer enters the vacuum state, the thin film formed by aluminum particles will adhere to the wafer. So, this process is called vapor deposition. And the next is the copper interconnection process. No? So, this process, with the improvement of semiconductor process, precisions, and the shrinking of device size, the connection speed and electrical characteristics of aluminum circuits are gradually unable to meet the requirements. For this reason, we need to find new conductors that satisfy the requirements of both size and cost. With its low resistance, so it can be achieved faster than connection speed. Now, what's more, copper is more reliable because it is more resistant to electromigration than aluminum. So, which is the movement of metal ions that occurs when current flows through the metal. No? So, there are instances na aluminum interconnect process won't be enough. So, we need to do the copper interconnection process. So that is all in the process of interconnection. So the next process is the test, no? So before good nato i-add to sa market or to proceed to the packaging, no? So we need to test first kung mugana ba ang mga electronics and semiconductors, no? So the main goal of the test is to check whether the quality of the semiconductor chip meets a certain standards, thereby eliminating defective products and improving the reliability of the chip. In addition, products are tested and defective will not enter the packaging step. No? So which helps to save cost and time. No, okay, it will be hassle kung pag humani mo package then na-receive sa customers or sa mga gabaligya and then there are defects, no? So it will be waste of time, no? So kubalik na sa factory to check and to no? So before nato gid siya after sa connection, pag na-connect na siya ang semiconductors sa iyang circuit, we need to test. Now there are 5 things, no, nga dapat nato i-test. And these are EPM, aging test, the repair, and the ink. No, these are the electrical die sorting. No, so first is ang EPM. Now it is the first step in semiconductor chip testing. So this step will test every device, no, including transistors, capacitors, diodes, and the semiconductor's integrated circuits needs to use to ensure that its electrical parameters meet the standards. So muna siyang una ang EPM. So diya nato pang testingan tanan transistors, capacitors, diodes, and other devices kung sulod ba siya sa standards. And next is the aging test or the wafer aging test. No, the semiconductors defect rate comes from two aspects, namely the rate of manufacturing defects higher in the early stage, and the rate of defects occurring throughout the life cycle afterwards. Now, wafer aging test refers to testing the wafer under a certain temperature and AC/DC voltage to find out which products may have defects in early stage. That is to improve the reliability of the final product by discovering potential defects. No? And third is the test. No? In parameters test, daghan ang gina-test diri, no? Including performance sa temperature, speed, motion test on the wafer through the probe card. No? So diri sa parameter test, gina-check ang temperatures. No? So unsa siya mag-react in regards to temperature. Maka-work ba siya in high temperature, low temperature, or in room temperature. No? So the high and low temperature test requirements for storage semiconductors are 85 to 90 degrees Celsius and negative 5 to 40 degrees Celsius respectively. No? So in speed test, ginatan-aw dyan ang core, ang speed, to check whether the core functions are valid, and to test the movement speed. And next is under sa test is ang iyang motion test. No? Gina-check ang DC, AC, and function. If apply direct current, to check whether the current and voltage are normal, and apply alternating current to test movements characteristics, and then check whether all functions are normal. Kay basin og na mga malfunctions and na mga defects regarding to pag-apply na sa direct current or alternating current. And fourth is the repair. Now, repairing is the most important test step because some defective chips can be repaired and you only need to replace the defective components. No? So, pag human sa APM, walay defect. Pag human sa wafer aging test, walay defect. Pag abot sa third nimo sa temperature or sa iyahang motion test is naka-defect. No? It doesn't mean nga ilabay na siya diretso. No? So there is a stage nga called repair. No? So in this step, gina-repair tong mga na-defect and then go back to the third test. No? So kung mo okay na ba siya. And then the last test is the ink. No? So the chips that failed the electrical test have been sorted out in previous steps, but they still need to be marked to distinguish them. Now in the past, we needed to mark defective chips with special inks to ensure that they can be identified with the naked eye. So today, the system automatically sorts them based on the test data values. No? So kung sa una pa, manually, ginabot niyan siya og ink to easily notice by the naked eye nga these chips are defective or gikan siya sa repair or na siya mga malfunctions. No? So that's all sa process sa test in manufacturing semiconductors before nimo siya i-package. So thank you for listening.
So my topic is package. Package is a square chips, also called single wafers or of equal size, are formed on the wafers processed by the previous several processes. The next thing is to obtain individual chips by cutting. The chip that has been cut is very fragile and cannot exchange electrical signals, so it needs to be processed separately. This process is packaging, including forming a protective shell on the outside of a semiconductor chip and allowing them to exchange electrical signals with the outside. The entire packaging process is divided into 5 steps, namely wafer sewing, single wafer attachment, interconnection, molding, and packaging testing. Wafer sewing. To cut countless densely arranged chips from the wafer, we must grind the back of the wafer until its thickness can meet the needs of the packaging process. After grinding, we can cut along the scribing line on the wafer until the semiconductor chip is separated. There are 3 types of wafer sewing techniques. First is blade cutting, second is laser cutting, and third is plasma cutting. Blade cutting refers to cutting wafers with diamond blades, which is prone to generate frictional heat and debris, and thus damage to the wafers. Second is laser cutting has higher precision and can easily handle wafers with thin thickness or small scribing line pitch. Plasma cutting uses the principle of plasma etching. So even the scribing line pitch is very small, this technology can also be applied. Here's an example video of wafer sewing. Second is single wafer attachment. After all, the chips are separated from the wafer. We need to attach the individual chips or single chip to the substrate lead frame. The role of the substrate is to protect the semiconductor chips and allow them to exchange electrical signals with external circuits. A liquid or solid tape adhesive can be used to attach the chip. Number 3 is bond. After attaching the chip to the substrate, we also need to connect the contact points of the two to achieve electrical signal exchange. There are two connections methods that can be used in this step. First is wire bonding using thin metal wires and flip chip bonding using spherical gold or tin blocks. Wire bonding is a traditional method and flip chip bonding can speed up the semiconductor product manufacturing. Fourth is molding. After completing the connection of a semiconductor chip, it is necessary to use a molding process to add a package to the outside of the chip to protect the semiconductor integrated circuit from the external conditions such as temperature and humidity. After the packaging mold is made as we required, we put the semiconductor chip and the epoxy molding compound or EMC into the mold and seal it. The sealed chips is its final product. 5. The package test. The chip that has a final form must pass the final defect test. All that enters the final test is the finished semiconductor chip. They will be put into a test equipment that set different conditions such as voltage, temperature, humidity, etc. And for electrical and functional and speed tests, the results of these tests can be used to find defects, improve product quality, and production efficiency. And that's all. Thank you.